Hi guys, it's Daniel here, and today we're going to do 2012 AMC 12A number 25. So let's first read the problem. Let fx equal the absolute value of 2 of the fractional part of x minus 1. And we have a number n such that it's the smallest positive integer such that the equation, this random thing, has at least 2012 real solutions. What is n? So this problem, at first it looks like it's pretty much impossible to do. Like, okay, let's just try putting in the definition of f of x into this expression and see what we get. We have n times f of x. So that would be the absolute value of 2 times the fractional part of x f of x, which is x times 2 times the fractional part of x minus 1. That taken the fractional part minus 1, absolute value again. This equals x. And we want to find the smallest positive integer n such that this equation has at least 2012 real solutions x. And already this seems like it's unapproachable. And I honestly have no idea how to solve it like this, because it's just too complicated to even have any sort of method to solve it. So we know that directly plugging in f of x, the definition of f of x, into our equation and trying to solve definitely will not work. So we have to find some sort of other way to solve this problem. And one thing you can notice is that we're not asking for what the exact specific values of x that solve this problem are. We're just asking for at least 2012 real solutions to x. So because we're asking for something a little bit more general, not the actual solutions, we can sort of make approximations. So that's our first observation. Make approximations. Make approximations. So now that we have something that we might be able to use, the fact that we don't have to do everything exactly, let's first just see what f of x actually is. So I'll first graph f of x equals 2 times the fractional part of x minus 1, and then we'll take absolute values after that. So here is the graph of f of x without the absolute values. Without absolute value. Alright. So if we plug in x equals 0, we get negative 1. X equals 1/2 gives 0. And x slightly less than 1 gives 1. So this part looks like that. And then after that, because the fractional part repeats, the graph kind of looks like this, as such. And now once we take the absolute value, so fractional part with absolute value, we get this sort of multiple triangular shape, where the base of each triangle is 1 and the height of each triangle is 1. So this is our graph. I'll draw it in a different color. This is the graph of f of x. So now we know the graph of f of x, and well, since there really isn't much else we can do, let's try to find the graph of x times f of x. So this will be quite a bit harder, but with our observation to make approximations, it should be easier than you actually think. So of course, when x equals 0, let's actually just do casework on which interval we're using. So instead of multiplying this entire thing by x, we can just multiply each of these sub-intervals, which only consist of a line, by x, and then it'll make it a little bit easier to graph. So let's see, in this first subinterval, the equation is, this equation is 1 minus 2x. And if we multiply by x, we get something like this. And I'll create markings here, which denote 1/2. So this has a scale of 1/2, and I'll draw a scale of 1 on the y-axis. So so this first part is alright. What about the second part? Well, this equation right here is 1 or -1 plus 2x, which implies that the graph will look something like this. And if we plug in 1 into -1 plus 2x times x, then we get times x. This equals 1, so that means this point is 1, 1. And now we can repeat the argument again. This next line is 3 minus 2x, which gives something like this. And then the next line is -3 plus 2x, which gives something like this, which ends at 2, 2. And note that other than this first interval from 0 to 1/2, my drawings aren't exactly accurate. These are supposed to be parabolas, but I've sort of drawn them as only straight lines. Because, again, we can make approximations. Because we don't need the exact numerical data in order to find the number of real solutions x this equation has. So, in essence, this graph x times f of x kind of just looks like a graph in which you have something like small right here, and then after that you have a bump to 1, 1, and back down, a bump to 2, 2, back down, a bump to 3, 3, back down. And the base of each of these triangles, they're not really triangles, but the base of each of these is 1. So why didn't I draw the negative x-axis as well? Well, note that at the end we have f of x equals x over n, and we want to find the intersections of these. Well, the right hand side is just a graph that looks like this. The left hand side, well, it's f of something, and f of something is always positive because by definition we're taking absolute value, so it'll do something like this. But then, of course, it's impossible to have any intersection on the negative x-axis because the x over n is negative and f of something is positive. So, in fact, I just need to check what the positive values of this weird function x times f of x are. So once we have this positive part of x times f of x, we can again apply f to this equation, and then we'll be able to get this random graph right here. And hopefully it won't be that bad. So at the start, it goes up to like, I don't know, 1/4 and goes back down to 1. So if we use the graph of f of x as a reference, I'll just draw it again right here. It starts at 0, so the graph of f of x will start at 1. It goes to 1/4, which is around here, and then goes back up to 1. So the start of the graph will look like this. And again, I'll give 1/2 markings. Alright, so the beginning looks like this. And thankfully, this weird beginning part won't actually matter because our line will look like this. So it won't actually intersect this beginning part. And that's fortunate for us because the rest of the graph will actually be quite easy to visualize. Again, using the make approximation idea. So now that we have the first 1 to 1/2 interval, let's look at the next 1 to 1/2 interval. This goes to 1, so the graph should go to 1, which is right here, and then go back to 0. So at this point, at 1/2 to 1, it should go down to 0 and go back up to 1. So something like this. And then at the 1 to 1 1/2 interval, it goes back down to 0 right here. So this should go back down to 0 and then back up to 1, like this. And now this 1 1 1/2 to 2 interval, it goes up to 2. So it goes down to 0, up to 1, down to 0, up to 1, all the way to here in this 1/2 interval. So down, up, and then same thing when we go back, we go down, up twice. Now this one goes to 3, 3, so it goes up 3, so that means it goes down, up to over here. So we have down, up, down, up, and then we see that if we keep on going, it goes down, up, and then it just keeps on increasing the number of oscillations by 1. So if we record how many oscillations we have here, we have 0, we go down once and go up once, so that's 2, and go down once, go up once, that's 2, go down twice, go up twice, that's 4, 4, 6, 6, 8, 8, and so on like that. And this number is also the number of intersections of x over n with f of x. As you can see here, we have 1 intersection, 2 intersections, 1 intersection, 2 intersections, 4 intersections here, 4 intersections here, and so on like that. So now all our job is to find the n such that if we add 0 plus 2 plus 2 plus all the way up to the nth unit, then we will get over 2012. So let's try to enumerate what our sum will be at any general n. So at n equals 1, we have 2. At n equals 2, we have 2 plus 4. At n equals, or not 2 plus 4, 2 plus 2 plus 4. At n equals 3, we got 2 plus 2 plus 4 plus 4 plus 6, and so on like that. So if we look for a pattern here, we see that 2, 4, 6, that's the sum of the first n even numbers, and 2 and 4 is the sum of the first n minus 1 even numbers. Recall that the formula for the sum of the first n even numbers is n squared plus n. So the sum of the first n minus 1 even numbers is n squared minus n. So the total number is 2n squared. So when we pick a general n, the number of intersections of x over n with f of x is 2n squared. So now we're almost done here. We just want 2n squared is greater than 2012, which means that n squared is greater than 1006, which means that n is greater than or equal to 32. We look back, is this an answer? Indeed it is. So C is the correct answer, and we are done. And last video we did a problem from an anime called Madoka Magica. This video I'll solve a sort of generalization